So, welcome everyone, and welcome to this session called The Edge of Chaos, the Dynamics of Directly Imaged Exoplanets. I would like to introduce to you Clarissa Duo, and she's a PhD student at UC San Diego, beautiful San Diego. And she's in the third year, very smart woman, and she's going to talk to us all about direct imaging. We've heard such a talk before, but Clarissa is going to give a different angle, and there are many different methods. So Clarissa, welcome. I hope you're going to be okay now.
Hello. Yes. Thank you for having me.
It's so nice having you. I know poor Clarissa, she was quite flustered because, well, she had the typical thing that before you start, your computer crashes and so on. So have a little patience with her. Everything's going to be fine today. Okay?
Yeah.
Okay, it's all yours, Clarissa. We're looking forward to it.
Awesome. Okay. I'll be sharing my screen. Can everyone see this?
Yes, it looks good. It looks good. That's fine.
Yeah, so today I'm really excited to tell you a little bit more about the dynamics of directly imaged exoplanets. Before I get into the talk, I wanted to just briefly talk about myself. So I'm currently a third-year astrophysics PhD candidate at UC San Diego, and I'm particularly interested in the dynamics of directly imaged planets, which is what we'll be talking about today, and specifically on how we can use our current data to understand the orbits of these planets and their formation mechanisms. And unfortunately, it won't be the focus of the talk today, but I am also interested in building instruments to directly image these planets. And here I just have a couple of pictures of myself. So the first one is me working in the clean room, which is where I currently build some of the instruments that I'm working on. And the other one is me staring at Jupiter at the planetarium shows we give here at UC San Diego. Well, before I get into exoplanets, dynamics, and everything, I figured I should give you a little bit more context on what planets are, what exoplanets are, and how we can find them. I'm sure a lot of you are already familiar with this, but I think it's very helpful to just go back and look at the big picture before we look into something more specific. So first, let's define what a planet is and then what an exoplanet is, right? So here I have a screenshot of the planet definition from the IAU, which is the International Astronomical Union. So in 2006, the members gathered and they agreed that a planet is a celestial body that is in orbit around the sun. It has sufficient mass to have a nearly round shape, and it has cleared the neighborhood around its orbit. So with this definition, we look at the planets in our own solar system. So we have the terrestrial planets, which are closer to the sun. So Mercury, Venus, Earth, and Mars. Then we have our gas giants, Jupiter and Saturn, and our ice giants, Uranus and Neptune. And unfortunately, Pluto, which was considered a planet before 2006, no longer made the cut, mainly due to the third requirement. It is no longer considered a planet. But anyway, these are the planets in our own solar system. But exoplanets are planets that are outside of our solar system, and they're actually orbiting other stars that are not our sun. And you must be wondering, how do we actually find these exoplanets, right? So there are quite a few methods to find them. One method, for example, is called the transit method. So for this one, we look at the brightness of the star over time. And if a planet is passing in front of the star, or what we call transiting the star, we see a small dip in the star's brightness. And if we see that this dip is periodic because the planet is orbiting around the star, then we most likely have a planet around that star. We have another method for finding exoplanets called the radial velocity method. So for this method, we again look at the star. This time, we look at the spectrum of the star, so the component wavelengths of the star. And if you look at the system from an edge-on perspective, such as here, so we often say that planets are orbiting around the star, but really both the star and the planet are orbiting around the center of gravity of the system. And if you look at the system from an edge-on perspective, such as here, as the star is orbiting around the center of gravity of the system, it comes a little bit towards us and a little bit further away from us. And what we see in the spectrum of the star is a small blue shift when it's coming towards us and a small red shift when it's going away from us. And if we notice that this blue shift and red shift is periodic, that implies that we likely have a planet orbiting around that star. So these are two methods that we can find exoplanets. The third one, which is what we'll be focusing on today, we actually no longer look at the star. In fact, we want to cover as much of the star's light as we possibly can. We use for that a device called the coronagraph. And once we cover the light from the star, we try to look at the very faint light that's coming in from the planet that is orbiting around that star. So with this idea of the direct imaging method and the radial velocity method and the transit method, I had a poll question for you on whether you think, what percent do you think was of the exoplanets that were detected with direct imaging? So do you think it was more about 1% of the planets, up to 10%, 25%, or maybe half of all the exoplanets we have been found via direct imaging?
Okay, we'll give them about a minute. Think about this, and then I will share the results. Hey, we still got a few people missing. Don't be afraid to vote. I'm just looking. We've got 47 out of 54 so far. So okay, Clarissa, what do you think?
Yeah, pretty good spread. Yes, so it turns out that most of you, about 47% of you, are correct. It is about 1%. So out of the 5,338 total discovered exoplanets, about 66 have been directly imaged. So this is about 1.2% of exoplanet discoveries. And the main reason this percentage is so low is because directly imaging planets is very hard. So most of the planets, as I said, when we directly image planets, we are looking at the very faint light that's coming in from the planet, which means that all of the planets we actually see are still glowing from the heat of their formation. So they're very young planets. So here I have this plot, which direct imaging, in the direct imaging field, we constantly use. We like to call it a contrast curve. And essentially what this plot tells you is the contrast of the planet, or how much fainter it is than the star, as a function of separation here in arc seconds, so the projected distance of the planet from the star. And you can see here in the top right, here, these are all the planets that we have actually directly imaged. And one interesting thing you'll notice about them is that, first of all, they are at least 10 to the minus 6 in contrast. What does this mean? This means that all of the planets we see, they are at least, so they are all 1 million times fainter than their host star. Also, you'll notice that a lot of them are young. They're about 30 million years old, which means they're still glowing from all the heat of their formation, which we'll go into more detail in a second. And another thing you'll notice is that all of the planets we have directly imaged are gas giants. So they're at least 2 times the mass of Jupiter. If you wanted to image something like the Earth, for example, that would be extremely difficult. Not only because the Earth is very much fainter than the sun, it's about 10 billion times fainter than the sun, both because it is a lot smaller. Also, it's much closer to the sun, which makes it harder to see because you can get the planet lost in the star, in the glare of the star. And also, the solar system in general is a older system. We are a 6 billion year old system, give or take, while all of these planets are still very young. So here, if you put this in context with all of the currently exoplanet discoveries we have, here we have the period of the planet in days. And remember, the period of the planet from Kepler's laws is directly related to how close or far away it is from the star. So longer period planets are further away from their stars. And here on the y-axis, we have the mass of the planet in Jupiter masses. And you'll notice that most of the exoplanets we have discovered have been found either by transit or radial velocity methods. While for direct imaging, we have not found that many. But one thing you'll see from this plot is that even though we haven't found that many, we do see a different type of population of exoplanets. We look at planets that are, as I said, are very young, they're far away from their stars, and they're pretty massive. And that's the point that I like to always go back to, because it is just a very interesting population, because it does help us look a little bit more into the formation of these planets since they are so young. So here I have a few examples of some directly imaged planets. They were taken with the Gemini Planet Imager, or GPI for short, which is the instrument I currently work on for my thesis, but will not be the focus of this talk. And essentially the way it works is, as I said before, we try to cover the light from the star. Here the stars is in the center and it's being covered by the coronagraph. And here we have each of the planets being shown in arrows. So we have 51 Ari B, HR 2562b, HR 8799c, D, and E, and Beta Pic B. And one thing you might already notice from how astronomers like to name their exoplanet systems is that we have a bit of these telephone number style names. And then whenever we find a planet, we essentially just give the planet a letter. So for example, HR 2562 is the star, HR 2562b is the planet orbiting around the HR 2562 star. So as I said before, one interesting thing that we can do with these directly imaged planet systems is we can try to understand a little bit more about their formation because they are so young. So most theories suggest that exoplanets, or planets in general, have formed from what we call a protoplanetary disk. So that is just a structure that is shaped like a disk, and it's mainly made of gas and dust that's orbiting around the very young star. And as the system evolves, we eventually see these very young planet systems. This is the HR 8799 planet system, which is about 30 million years old. We'll go back to the system. It is a very special and interesting system. So don't worry about that. We'll talk about that. But the main thing right now is that we can try to understand how the details from protoplanetary disks, here this disk is about 100,000 years old, to a fully formed planet system about 30 million years old actually occurs. We are still trying to understand the details of these mechanisms. So there are two main formation theories for planets. So one of them is called the core accretion model. In this one, we have the protoplanetary disk, mainly made of gas and dust. And as it orbits around the host star, there are small dust grains that begin accreting into planetesimals, mainly through non-gravitational forces, which means there are small dust grains that sort of stick to each other as they orbit around the host star. And as they orbit around the star, these planetesimals continue to get more mass onto themselves, and they become planetary embryos. And this explains pretty well how rocky planets form. But for gas giants, there's an extra step where after they have accreted enough solid material, enough dust, they actually start accreting gas onto themselves. And they have that gas envelope that we see even in the gas giants in our own solar system before the gas disk has fully disappeared. And then finally, we have our fully formed planet system. Then the other main formation theory is called the gas collapse model, or gravitational instability model. So here we again have the protoplanetary disk, mainly made of gas and dust. But instead of having a planet slowly build up from all of that dust that is slowly accreting, we actually have a instability in the disk, a gravitational instability in the disk that forms a clump of gas that becomes a self-gravitating planet. And this newly formed gas giant continues to orbit around the star in the protoplanetary disk, and it actually ends up carving a gap in the disk as it obtains more gas onto itself. So how do we understand a little bit more about the formation of these planets from finding out more about the orbits of these directly imaged planets? So one interesting parameter that we like to look at when we look at the directly imaged planets is the eccentricity of the planet. The orbital parameters in general can tell us a little bit about how the planets formed or interacted with each other. And the eccentricity is a very special parameter. It essentially defines whether your orbit of the planet is more circular, which would be an eccentricity of 0, or is something more elliptical, and it can go all the way up to 1 for a bound orbit, but here on the drawing only goes up to 0.8. And more often than not, we can see, given the eccentricity and also other orbital parameters, how the planets actually interacted with each other very early on from formation. So here I have a drawing of an orbit. When we try to look at the orbit of a planet, an exoplanet, we actually have to remember that these planets are all in 3D space. So there's actually 6 parameters that define the orbit of a planet. So we have the period, which is just essentially tells you how long the planet takes to fully go around the star. So for the Earth, for example, we have a 1-year period. Then we have the eccentricity, which defines again whether this orbit is more circular or whether it's more elliptical, and that can go from 0 to 1. Then we have the inclination of the planet, so of the orbit of the planet. So that essentially tells you whether, if you're looking at a planet, whether its orbit is more face on when we look at it or more edge on. And then we have another parameter called the longitude of ascending node. It's a very fancy name, but all it really does is it's an angle that is the second angle that defines the plane of the orbit. So there are 2 angles that define the plane of the orbit, the inclination, and the other one is longitude of ascending node. Then we have the argument of periapsis, and this angle just tells you where the planet will be when it's passing closest to the star. And finally, we have the epoch of periapsis passage. So that is when the planet will be when it's passing closest to the star. And with these 6 orbital parameters, we can essentially find out what the orbit of the planet is. And that helps us with constraining a little bit more about how they formed and about their dynamics. And the way we actually find that out is by measuring the positions of these planets, which we call the astrometry of the companion. And essentially the way it works is you are looking at the planet, suppose at time t, and you record its position relative to the host star to be x and y. And then you come back a few years later and you measure the position of the planet again, this time at t prime. And it's now at position x prime and y prime relative to the host star. It has moved because it's orbiting around the star. And by having measured the positions of these planets, we can then try to fit for the possible orbits of the planets. And because we are dealing with 3D space, there is quite a lot of range or variety in what you can have. So you can have orbits that are more edge on, more face on, more elliptical, more circular. And essentially with that, we can just try to constrain what are the possible orbits of the planet and where the planet will likely be in the future. Okay, so we know the orbits of these planets. And now what? What do we do with that? So one interesting thing we can do is we can learn about their stability and possible future. So I said we would go back to the HR 8799 system because it really is the poster child of direct imaging for exoplanets. It is a very special system. So it is about 30 million years old, and it has 4 exoplanets, HR 8799b, which is over here, C, D, and E, and they are all at least 5 times the mass of Jupiter. So these are all 4 very massive gas giants, and they're all from 15 to 70 AU. So the closest one is 15 AU, the furthest one is 70 AU. Again, to remind you, 1 AU is the distance from the Earth to the sun. So the closest planet in here is 15 times further away than the Earth is from the sun, and the furthest one is 70 times further away. So the way we can understand more about their stability from their orbits is by using what we like to call n-body simulations, which are just simulations on how these planets interact with each other gravitationally by solving the equations of motion for each of the particles over time. And if you know their orbits, this becomes a pretty straightforward thing to do. So when the system was first discovered, the HR 8799 system, there was actually a paper about a year after it was discovered that was titled, "Is the HR 8799 extrasolar system destined for planetary scattering?" So essentially what happened is these scientists ran n-body simulations for the system to see how it would evolve over time. And they found that most of the time, the planets would actually become unstable after 100 million years. And what this means is that when you would have the system evolving over time, you would have a few planets that would get crossing orbits, and then they would be ejected from the system, and others would go into a higher energy orbit, which would have a higher eccentricity. So all sorts of chaos were going to happen in this system. Anyway, this was a question that scientists had for a while because, we were seeing the system about 30 million years after it formed. So, it must have at least been stable until then. So there are a few questions on how this was actually happening. So before I get into how this problem was actually solved, I wanted to introduce you to this idea of mean motion resonance and orbital stability. So mean motion resonance or orbital resonance is a physical principle that we have in orbital mechanics. And you can think of it in the physical idea is similar to pushing a child on a swing. So you are periodically interacting with the child when you're pushing the child on the swing, and that eventually has a cumulative effect. What this means for a planet, for example, is that these planets, when they're passing closest to each other, they would gravitationally interact with each other periodically. And you can think of it as the pushing of the swing. And depending on the system, having a resonance like this can either stabilize or destabilize the system, depending very much on the specifics. So with this idea, I actually had a question for you on whether you think that in our own solar system, we have any sort of mean motion resonance or orbital resonance. So do you think we don't have any resonance at all in the solar system? Or maybe Earth and Venus are in resonance, so they gravitationally bump each other periodically? Or maybe Mars's moons, Phobos and Deimos, or maybe Jupiter's moons. So yeah, I'll give you a minute to think about that.
Yeah, absolutely fascinating so far, really. So let's see. So don't be afraid to answer. Let's see. Yeah, and you're already putting your questions and answer. I just wanted to say, I'm sure there are lots of questions coming up, and we'll keep them for later. So don't hesitate to put them in the Q&A section, please. Okay, we'll give it a few more seconds, and then let's see. Okay, let's stop the poll and I'll share now. What do you think, Clarissa?
Yeah. So as it turns out, yes, most of you are right. About 63% of you are correct. Yes. So we do actually have resonance in our solar system. It's Jupiter's moons, specifically Jupiter's Galilean moons, Io, Europa, and Ganymede. They are in a 1-to-4 mean motion resonance. And the 1-to-4, all it really means is that the periods of these moons are perfect ratios of each other. So every time that Ganymede goes around Jupiter once, Europa goes around Jupiter twice, and Io goes around Jupiter 4 times. And you can see here what I really like about this movie is that it actually shows you where the planets interact due to the resonance. So it blinks in green every time that Io and Europa have interacted, in white every time that Io and Ganymede interact, and it also blinks in pink every time that Ganymede and Europa interact. And that you can notice that's always when they're passing closest to each other. And that's the little bump, the pushing of the swing that we see in resonance. And one interesting thing about our solar system is that we actually have all sorts of resonance in our solar system, is not just Jupiter's moons. So for example, Pluto and Neptune are in resonance. They're in a 2-to-3 resonance. And all this really means is that every time that Pluto goes around the sun twice, Neptune goes around the sun 3 times. And Saturn's moons, for example, Dione and Enceladus, are also in a 1-to-2 resonance. So every time that Dione goes around Saturn once, Enceladus goes around Saturn twice. But we actually have all sorts of resonances in our solar system, from the moons to rings. Saturn's rings have resonances, asteroid belts. So really, we are just filled with that in our own solar system. And one interesting thing about this is with direct imaging, we can trace that back to formation. So I wanted to give this very specific example of the PDS-70 system, where we see formation happening live, so happening right now. So this system, the PDS-70 system, is very young. It's 5 million years old, and it has a protoplanetary disk, but it also has 2 embedded planets in the disk that are forming right now. So PDS-70b and C. And one thing you'll notice that's very interesting is that the period of these planets are 100 years for B and 200 years for C. I hope you will start seeing where I'm trying to get to here, where they're about ratios of each other of 1 to 2. And yeah, we can actually trace this back to formation by trying to simulate how these planets actually formed in the protoplanetary disk. So Bay et al. 2019 is a paper that tried to study how these planets evolved in the disk. In order to do this, actually n-body simulations are no longer sufficient because you have the two planets, but you also have the gas in the disk. And for that, you have to use what we call a hydrodynamic simulation. And that's just a very fancy name for trying to simulate the gas in the disk as well, because it does have a different type of mechanics from just having pure solid material. And Bay et al. 2019 essentially simulated these planets with the disk to see how they would evolve over time. And here I have an actual quote from the paper where they find that the two planets actually migrated towards each other and settled into the 2-to-1 mean motion resonance within the first 100,000 years of the simulations, and then they remain dynamically stable for the duration of the simulations. So here we have the simulations they made, and you can see the two little planets here and the disk. And here we have the evolution of the semi-major axis, which is directly related to the period of the planet. It tells you how far away the planet is from the star as a function of time in millions of years. And you can see here, PDS-7EB in the beginning of the simulation went a little bit further away from the star, and C went a little bit closer to the star, and they migrated towards each other. And then they essentially what happened is they were locked into this mean motion resonance, and they continued to remain stable for the rest of the simulations. And the reason I wanted to tell you about this is because it turns out that resonance is what solves the problem of HR 8799. So remember, I told you a little bit of a sad story about how scientists were trying to understand how the system would even remain stable in the first place. We had planets being ejected and going all over the place. And it turns out that a resonance of 1,248 allows the system to be stable for at least 160 million years. So here, what this means is that the outermost planet, when it goes around the star once, then planet C goes around the star twice, D goes around the star 4 times, and E goes around the star 8 times. And essentially, the simulations done by the same scientists actually who published the first paper in 2009 is that they found that HR 799 likely formed from a very unusually protoplanetary disk, mostly through gravitational instability, but the planets actually migrated together to a resonance configuration pretty early on, about as early as 10,000 years old. So it turns out that resonance can be one solution for the dynamics of these systems, for them to actually be stable, because they interact so much with each other that they end up being locked in this resonance. So before I finish the talk and we can all address questions, I actually wanted to have a quick slide on the current research on exoplanet direct imaging. There is quite a lot of work going on in this field. It's a very young field and very exciting to currently be working on it. So here, we're currently trying to understand a little bit more about planet formation using protoplanetary disk simulations, as I showed you, also fitting data, and trying to understand more about the orbital architecture of these systems, both from a stability perspective and also other possible constraints. We're also assessing even the statistics of orbit fitting to see how we can improve our fits to the data and have better constrained orbits. We're also working on trying to improve our current instruments or building better instruments such that we can get closer to the star and find fainter planets. Also, there's a lot of work going on the actual post-processing of these exoplanet images. So some of the images I showed you actually had a lot of post-processing happening before we actually see the image that we just saw. And also, there's a lot of work going on in characterizing the atmospheres of these planets to search for planet formation clues or even biosignatures. And I have highlighted in asterisks the things that I personally work on. But we actually have many more things going on in direct imaging, hopefully with the idea that one day we can actually directly image something like an Earth-like planet around a sun-like star. And I'd like to remind you of, us. So our little pale blue dot over here, this is us. This is the Earth being seen from about the orbit of Neptune with the Voyager spacecraft. And, hopefully one day we can image something like this going around a different star. And that would be very, very exciting. So in summary, if there are two things I think that hopefully you will have gotten away from this talk, is that planets form in disks, and we can use their orbit fits to understand a little bit more about their dynamics and their formation. We can also understand more about their present and even their future. So whether they go into chaos or they remain stable for millions and millions of years to come. And with that, I would like to thank you, and I will gladly take any questions.